Hello everybody. Today we are going to present the first part 1 of Lab 3. There may be some confusion with the names. This is sometimes called Lab 3B or the lab before Lab 3, but to keep all that aside, we'll just call it part 1. In this lab we are going to do a impulse response using the GP6 by the method of correlation analysis. So what we do in this lab is that first you get the model in continuous time from the K and tau that you got in the previous lab, which is this right here. Once you have that model, you use the C to D command in MATLAB and you get a discrete version in the Z domain, and you find the impulse response of this in order to get what we want, because we want the impulse response. Now when you specify the impulse response, it asks you for a length. Please note that in this lab we will call all lengths with capital N or big N, and big N has to always be a power of 2. Okay, so it has to be like 16 or 32 or 512 or 1024. A good number to start for with big N is around 256 to 512. Okay. There is a command in MATLAB called ID input. We are going to generate a pseudo-random binary sequence or a PRPS signal, which is nothing but a randomly repeating sequence of plus ones and minus ones, which has a zero mean. It is basically white noise. The reason we call it as white noise is because it's zero mean, and therefore if you get the FFT of it, it will have all frequencies in it. The reason we use this kind of a signal to excite our system is because in order to do system ID, like to get a correlation analysis or do least squares, which we'll do in the labs after this, we have to meet something called the persistent excitation criterion. And if you don't excite your system enough, then you will not get good data. So here's what we do. We generate the ID input command, and this block that you see, PRBS, is actually a from workspace block. That block takes a matrix. The first row of the matrix is the time, and the second row is the PRBS input. Sorry, I'm saying row, it's the column. So in the first column, what you do is you put the time vector. So your time vector is going to go from 0 to 0.01 to n times ts, where ts is your sampling time. So it goes at steps of ts till n times ts, which will give you the length of time for which the experiment needs to be run. This is a discrete transfer function block, az by bz. Okay. Do not use a continuous transfer function or any other transfer function blocks, because that will mess it up. You may need to specify the sampling time in here. The output is just a scope. And in this lab, what we do is we first get the simulation model like this one, and we pass a PRBS input into it and get an output from it. This is all in Simulink. We are not using Quanzur or we are not using GP6s yet. Then you write code to evaluate the impulse response using the correlation analysis. U is your input vector, which is the PRBS signal. Y is your output vector, which came from this output. And you have those two summations. And lambda is 1 because this is a white noise, and if you look up the formula you will see why that's happening. And n, big N here, is the length of your PRBS signal. Okay, and g of tau will be your impulse response. It will be a vector. Tau is just a variable. It is not the constant of the motor. It can be called any other variable. This is like kind of like convolution happening here to make things easy a bit, but do not get confused overly with it. There's nothing complex going on really. And okay, once you have got g of tau, So here's the steps what you need to do first before you get GF down. Get your PRBS signal, give it an appropriate time vector. Before that, you should have your numerator and denominator of the motor model, the discrete version, plug it in here. Connect these two blocks, give it an output, run it in Simulink for the time which is n times ts. Then you get a vector called u. Take your vector u and your vector y from this model. U is the PRBS, y is the output. Plug it in this formula, write code to calculate g of tau. And then you plot g of tau. It should look like an impulse, it should have a peak and then it should slowly flatten out. And for this lab or for any lab where you use discrete vectors or discrete operations, when you plot the results, you use the stairs command in MATLAB and not plot, because that may give you errors. Okay, so that was the step one. The second step is fairly easy. We did the modeling of the motor using the GP6 in the previous lab. So all you need to do is just repeat that lab.
Yeah, we need to use just the same configuration.
The same configuration, every connection is the same, the part settings are the same because you're modeling the motor again. And then just hook it back to the quantum system. Only difference is this time you will pass the PRBS signal to the GP6 and get a new data set. That will be your new data set, say Y1. And then you will use your U and your Y1 to get a new impulse response. We call it, say, G1. And then you will superimpose the G1 that you get from the GP6 and the G that you got from your Simulink model and see how closely they match. Thing to note is that it is not required that the trailing part which drops off of the plot, it should not match, but the peak of the impulse should match very closely if you do the math right. And there are factors in this based upon the sampling time and the length of time you run and the length of the PRBS. So this experiment needs to be repeated over multiple cycles for different ends of the PRBS length and different sampling times. And you will see that some of them perform better, some of them perform worse. The job in this lab is to find out the range where it works the best, and then just have the comparative plots between your Simulink and your GP6 ready so we can see what's going on. That's it, and my friend will now show you how to get this setup up and running.
Hello everyone, and now I'm going to show you how to do it in MATLAB. So first, as my friend says, Shayot, we need to use the same K, DC gain K, and the tau that we have from previous lab. So those are the values that we have before, so we need to use it in this lab. After that, just we need to calculate the transfer function, and then using the command C to D, we transform this transfer function in a C transform, in a discrete transform, because we need to use it in this lab. And after that, we need to use the TF data command to get the numerator and denominator of the C transform in order to get this block right here, because we going to simulate the C transform of the motor. I mean, it's gonna be a simulation part, right? So we need the C transform is gonna be the numerator and denominator. This is the block. And to generate the PRBS input, it's gonna be like that. So if you don't know how to use this command right here, the ID input, so you go to MATLAB and just type help and the name of this command, and MATLAB is going to show you how to use it. So it's really easy just to read, and MATLAB is going to show you how to use it. This is U, N, and the band, the labels, something like that. So this command is going to generate like a random